This is a question from complex analysis, and this is a part C question from June 2019 CSIR net mathematical science examinations. This is a question number 80. So let's see the question. Let RZ and INZ denote the real and imaginary parts of Z. Z belongs to the finite complex plane C respectively. Consider the domain omega or big omega equal to Z belongs to C such that RZ strictly greater than modulus of imaginary part of Z, and let fn z equal to log z to the power n, where n belongs to 1, 2, 3 and 4, and log is the function whose domain is c minus infinity to 0 close to c, defines the principal branch of logarithm. Then which of the following are true? Image of omega under f1 is z belongs to c such that 0 less than equal to modulus of imaginary part of z less than pi by 4, and option 2 is the image of omega under f2 is z belongs to c such that 0 less than equal to modulus of imaginary part of z less than strictly pi by 2, and image of omega under f3 is z such that 0 less than equal to modulus of z modulus of imaginary part of z strictly less than 3 pi by 4, and last option is f4 of omega is z belongs to c such that 0 less than equal to modulus of imaginary part of z strictly less than pi. So let's first of all see what kind of the domain this omega is. The omega is omega such that z belongs to c or finite complex plane such that z or real part of z strictly greater than modulus of the imaginary part of z, or we may write z in the form x plus iy. Then from this relation we can write x greater than modulus of y greater than equal to 0, and from this we get a rough idea about omega. If we represent this graphically, this is what looks like. This purple color region indicates omega, and the origin and the line z equal to r e to the power I pi by 4 r greater than 0 does not include in the region omega, because in omega the real part of z, that is x, is strictly greater than y. Also we find from this picture that argument of z satisfies this inequality 0 less than equal to theta less than pi by 4. Now given the map fn z equal to log z to the power n equal to 1, 2, 3, 4, where log is the principal branch of logarithm. Now we will take a point from this big omega or the domain omega and see what its image under this map fn, precisely f1, f2, f3 and f4. So first of all we take for n equal to 1 the function is f1 of z equal to log z, and now we take a point z from this omega where z equal to x plus iy and satisfies this definition x greater than modulus of y, and its argument 0 less than equal to theta less than pi by 4. So under this f1 the image of z is f1 of z equal to log x plus iy, and from this definition of logarithmic branch, principal branch of logarithm, we can write ln modulus of this complex number x plus iy, that is root over x square plus y square plus I theta, where theta is the principal argument of z, and satisfies this inequality 0 less than theta less than pi by 4. So this is also a point in the finite complex plane, and ln root over x square plus y square is the real part of this point, and theta is the imaginary part of this point, which is the image of the point z, which is taken from this domain omega under this map f1. So f1 of omega is actually the set z belongs to C, the finite complex plane, such that 0 less than equal to imaginary part of z less than pi by 4, or we may write it 0 less than equal to modulus of imaginary part of z less than pi by 4. There is nothing harm to write this. In this way, if we take n equal to 2, we get the function f2z equal to log z square, where log is the principal branch of the logarithm. Then, and we shall again take a point from this omega z, and we see that the image of z under f2 is this ln x square plus y square plus I 2 theta, where 2 theta satisfies this inequality 0 less than 2 theta less than equal to 2 theta less than pi by 2, and this is also a point in the z plane, which is the image of the point z belongs to omega under the map f2, and this is ln x square plus y square is the real part and 2 theta is the imaginary part. So the range set f2 of omega, that is the image of omega under f2, is z belongs to C, 0 less than equal to imaginary part of z less than pi by 2, or we may write it 0 less than equal to modulus of imaginary part of z less than pi by 2. In similar way, under the map f3 and f4, we also find the domain range sets f3 of omega is z belongs to C, 0 less than equal to modulus of imaginary part of z less than 3 pi by 4, and under the map f4 the image of omega is z belongs to C, 0 less than equal to imaginary part of z strictly less than pi by 4. So all the options are correct options.